Hello, welcome. Okay, so what we're going to be working on today is going to be going in starting in on circular motion. Go ahead and just share the notes. And basically what we're going to be talking about is uniform circular motion. Now, to get started, I just wanted to give a couple of examples of circular motion. We'll get into what the uniform bit of this means in a second. But just and if you want, throw some examples of your own. Not just motion, circular motion. Throw some examples of your own in here in addition to mine. This will be kind of good to show, why we're doing this particular this particular unit. Planetary or satellite orbits. So these are probably some of the most common situations where uniform circular motion is going to get used. And uniform circular motion is not quite accurate. It's not quite adequate to describe these systems, but it does give you a pretty reasonable place to start. Anything like a rotor, so like a helicopter rotor or anything, any kind of tool that's going in a circular, it's moving in circles. Things like a turbine or a wheel, maybe. Kind of anything like that. Now, you might say, okay, fine, it'd be helpful to analyze these things, but here's the other thing is that if we had, say, like a road that looked like this, and we'll do it. Oh, that's not so good. Okay, try. That's a little bit better. And we say that we've got this curve in the road. Now, we wouldn't necessarily say that that's a circle. However, turns out physically what we can do is we can approximate this portion of the curve as a circle. Okay. And we can apply a lot of the lessons we learned from analyzing circular motion to that curve in the road. And it turns out to be quite useful in terms of doing these kinds of analyses. Okay. So that's one of the things that we're going to be looking at. So I think this last one is really the most important. This is really any curve in motion. Now, some curved motion, we find it easier to analyze in other ways, like, for instance, projectiles. Those followed a parabolic curve, and it's just easier to analyze those as parabolas rather than as, sequentially different parts of a circle. But but a lot of times when we have a curved path like this, where we have just like a road or something like that, or a turn. You imagine yourself going through a stoplight, and you turn. It's not like you go straight and then immediately change directions. You do this kind of soft turn that could better be thought of as sort of a quarter circle when you're thinking about the path. It's much closer to a quarter circle than it is straight stop and then immediately turn and go the other direction. So a lot of times these things can be thought of as parts of circular motion. Now, to get into uniform circular motion, basically what we mean by uniform circular motion is that this is we're going to be looking at the simplest system undergoing circular motion. And generally, this is going to have three attributes. The first is we're going to look at a single mass. Now, this would be contrasted against something like a propeller, where you could say a propeller would be going in circular motion, but the mass of the propeller is distributed all up and down it. Basically, when I talk about a single mass, basically what I mean is that we're looking at this object as going in a circle, and all the relevant mass is just kind of at a single point in space on the path of the circle, rather than distributed up and down and then all kind of going in circles of their different size. So the difference here would be a propeller would have, that would have mass, distributed all up and down the propeller. But if you were, on the other hand, if you were taking like a yo-yo and swinging that around in a circle, most of the mass would be out on the yo-yo. Like the mass of the string would be, basically negligible compared to the mass of the yo-yo is the idea. And then the other thing, obviously, from the second word, it's traveling in a circular path. And finally, the last aspect is it's going at a constant speed. All right. So if I tell you what I'm going to do, I'm going to grab the circle from the notes because I'm just not good at drawing circles. All right, so there we go. So basically what we have here is we would have, let's just say we're going around clockwise like so. Basically, the idea is that any point we pick, we would have, some velocity. And this, at the top, it's going directly to the right. Now on the right, it's going directly down. At the bottom, it's going, well, that kind of angles it, but it's going directly left. For those of you familiar, the velocity is actually tangential to the circle, the velocity vectors at any given point. But this constant speed, what this means is all velocity vectors have the same length. Now, I've kind of given this problem away, but I'm going to ask the question. Does this mean velocity is constant? Now, again, assuming these three conditions are true, and I'll go ahead and circle them. Circle them in blue. These are the three basic conditions that we're going to be looking if something is going to be undergoing uniform circular motion. Does this mean that velocity is constant? I'd answer this question for yourself and then see if you're right. So answer, yes or no, and try and come up with a reason why. It turns out the answer is no. Velocity is not constant. And the reason why velocity is not constant is because, oh no, if I could ever get back there. Because velocity changes direction. And remember, in order for velocity to be constant, it not only needs to maintain the same magnitude, which it does in this case. In this case, velocity maintains the same magnitude, meaning the same speed. But because it's constantly changing direction, this requires an acceleration. Okay, and this was actually why I requires an acceleration. This was actually why I wanted to show, or why I asked the question, is velocity constant? Because what we're going to want to do is we're going to have to find some kind of acceleration here, okay? And the idea here is that force is required to change the velocity, and that includes changing its direction, okay? And you can kind of imagine, what happens to a yo-yo if it's going around in a circle and the string breaks. It doesn't keep going around in that circle. There's something about the string attached to it that was causing it to continue to go in the circle. Now you are also, giving it. You were also giving it little, with your wrist, you're giving it little pushes, but for the most part, like if the string breaks, the thing won't just go in a circle, it'll fly off in basically a straight line. Honestly, in a straight line indicated by whichever arrow the velocity is pointing at when the string breaks, okay? So it turns out that you need to have a force. Now, if you thought no, this was going at constant velocity, and so there was no acceleration, well, you are in reasonable company. Galileo thought the same thing. It's why he couldn't really make the connection between forces and the force of gravity and the rotation of the orbits. So no harm. But the point that's important is that yes, if you're going in a circle, you are always going to have acceleration, even if you're going at a constant speed. Okay. So question then is, what is the magnitude and direction of the acceleration? Well, I'm going to try and demonstrate this on another diagram, kind of similar to this one I just did. So can I copy it and then paste it? There we go. Okay. So the idea here, and I'll do my velocity vectors in purple. All right, so what we have here going from before is we have V1, and I'll try to make that indicated kind of like so. Now, at some time, a little bit of time later, like right here, we'll have a V2. Now, it's important that V1 and V2 have the same length. So V2 right there. Those are the two different velocities, and they are different because they're pointed a different direction. But V1 and V2 have the same length. Now, the way we indicate that, another way of saying that is would be they have the same magnitude. Now, the way we can indicate that is this absolute value. That just means the magnitude of the vector. And I'm going to write that as V. Now, the idea here is that the magnitude of either one of those vectors represents the speed, which is constant. That's how we know they have the same length. Okay, that was the definition of uniform circular motion. All right. But another thing I'm going to do is I'm going to try and find the center. That's pretty reasonable for the center right there. And then I'm going to let the center be my origin. So we'll just call that the origin. And what I'm going to do is I'm going to draw a position vector at these 2 points. And I'm going to label the position vector R instead of X. X doesn't make as much sense since it's constantly going in 2 dimensions. But that would be R1 and that would be R2 right there. All right. Now, the important thing to note here is that the velocity vector is perpendicular to the r vector. Okay, so that is something worth keeping in mind. Now, as I've drawn R1 and R2, these are tail to tail. Now, hopefully you remember, and I'll change this to red, I guess, for that. But hopefully you remember that if I draw, if I put one, if I use this tail to tail method, what that is a subtraction. So what that has there, that would be R2 minus R1, and we call that delta R. Well, why is that relevant? Well, as a reminder, it's worth knowing that the velocity vector, I'll bring that back to purple actually. The velocity vector, and this would kind of be the average velocity between those two. But it should be equal to the delta R vector over delta T. Now, what this should mean is you should just be able to take magnitudes of this. So we should be able to say that V is equal to delta R over delta T. Now, that is going to have some relevance because what I'm going to do now is I'm going to try to I'm gonna try and transpose these over to here. Okay, so what you have here is you have your velocity 1, try and keeping that at the same length, but instead of but what I'm going to do now is I'm going to put velocity 2 on the same point, the tail of velocity 2 on the same point as velocity 1. Okay, and it looks kind of like that. Trying to do this freehand the best I can, and maybe successful or not successful. So that was V1, that was V2. Now, like those should have been vectors there originally. What I'm going to do is instead of having them both be V1 and V2, I'm going to have them both just be V. And again, this is reminding ourselves that these things are the same length and vector. Now, another thing important to know for R1 and R2, the magnitude of R1, actually, I'll write this below. Magnitude of R1 should be equal to the magnitude of R2, which should be equal to the radius of the circle. Okay, so that's fine. It's going to be something important, but it's worth putting that underneath it that we just have R and R as the length of those sides. Okay, so hopefully you can see that both of those black arrows that I've drawn would have a length of R, which is the radius of the circle. Now, the key thing here, I'm going to change to, actually, we'll change to green, is that basically this vector right here, that represents V2 minus V1, that green one. Now, as a reminder, this is also delta V, and acceleration is equal to delta V over delta T, which means that acceleration will point in the same direction as delta V. I'll put that. Acceleration points in same direction as delta V. Okay, so what we can do now is we can transpose this back to the circle. Now, as to where we should put it, the best place to put it is right halfway in between the two velocity vectors. So I would put it right there, and then you draw it kind of like so. And, it's not perfect, but you can kind of see that, okay, delta V is pointed straight at the center. Okay, and that means acceleration is pointed towards the center, pointed towards the center of the circle. Okay, and this is going to be a really important thing to know, that vectorially your acceleration is always going to point towards the center of the circle. Now, depending on where the object is, that could change. Like, that direction could change. Like, if your object is where I drew it, then it's kind of pointing mostly down, a little to the left. If my object was at the bottom of this circle, then the change in velocity, or the centripetal acceleration, well, I didn't get into centripetal, but the acceleration itself would be pointed straight up. Okay, and I might as well define that term. A sub C stands for centripetal acceleration. And the reason it's called centripetal acceleration is it means it's directed towards the center. We'll get into this idea of centrifugal. Centrifugal is generally applied to force, not so much to acceleration, but we'll get into that in the next lecture. So today we're mostly going to focus just on centripetal acceleration. Now the question is, okay, what can we find the value of the centripetal acceleration? And one thing that's worth noting is that we can actually, and we'll talk about why that's the case. But what we can say is that angle is theta, and this angle right here is theta. And the key thing that makes that relevant is that what I've effectively drawn in the original circle with two black legs and a red leg, or a red base, I should say, is a triangle, an isosceles triangle with angle theta. The triangle with two purple legs and a green base, that is also an isosceles triangle with an angle theta. So the point here is that these two triangles are similar, meaning they will have the same proportions. All right. Now, why is that relevant? Well, what I can say here is I can say, okay, I can do a ratio of the sides. So in the black and red triangle, I can say, okay, delta R, that's the base. I'm going to put that over R, which is one of the legs. Now that's just the length. I'm not doing vector things, but the base is delta R and the length is R. And I can do the same thing with the purple and green triangle. I can say delta V is the base, and V, the speed, is the leg. So I'm gonna bring that down to here. So delta R over R is equal to delta V over V, just running out of space up there. Now I'm gonna do some substitutions. The first one is that delta R over delta T should be equal to our velocity if speed is constant. Okay? So that is worth knowing that as long as speed is constant, this is true. Okay? Now, why do I want to do this? Well, the more useful thing is going to be say that R is equal to V delta T, and then I'm going to do this substitution in here. So instead of delta R, I'm going to change that to V delta T over R. Okay? So that's what the left side becomes. Now, the other thing I can say is that delta V over delta T is equal to acceleration. Okay? And that's, again, it assumes constant acceleration, and this one turns out it will be. And now I'm going to move the delta T over there, so we get delta V equals A delta T. And this is how we're going to solve for the acceleration. Okay? So we're going to replace this in there, and we're going to get A delta T over V. Now notice what happens. The delta T's cancel out. And then I have V over R equals A over V. I can multiply both sides by V, and I get V squared over R is equal to A. And this is the formula that we are going to use for centripetal acceleration. V squared over R is equal to the centripetal acceleration. Now, in this case, V is speed, and R is the radius of the circle. Okay, so this really only applies to circular motion, and in particular, uniform circular motion. Okay, so that is what is going on with the centripetal acceleration. Okay, so this is going to be something that we come back to. Now, it turns out that you are going to need a force to generate this kind of acceleration. I'm not going to go into that just yet because that's more of a topic for tomorrow. But I do want to go through some examples of some things that can of finding the acceleration, the centripetal acceleration. Okay, so you might see an example like this. And like I said, a lot of them involve partial circles, not complete circles. So here's a couple examples like that. A car goes through a turn of radius 200 meters at a speed of 20 meters per second. What is the centripetal acceleration? Now, you could just kind of, given that you're given both the speed and the radius, you could just blindly plug this into centripetal acceleration, you get the right answer. But I do just want to be clear what we're talking about here. Basically, what we're talking about is that if we have a road like so, and the car is going along a portion of this road like so, the idea here is that if you turn this thing into a circle, now that's a very poorly drawn circle. It does, the road doesn't need to be in a circle, but for the portion that can be approximated with a circle, basically what you're saying is that R would be equal to 200 meters. Okay, so that's what it means when it says a turn with a radius of, a lot of times it's called it might just be radius. Sometimes you'll see a radius of curvature. In any event, it means like, if you were to extrapolate out a circle, that circle would have a radius of 200 meters, is what that's saying. Okay, so hopefully that makes sense. And then all you then need to do is just acceleration equals v squared over r, which would be 20 squared over 200, which would be 400 over 200, which would be 2 meters per second squared. And if you tried to make this circle tighter, your acceleration would go up. Alternatively, if you tried to go faster, your acceleration would go up. Okay, so that's the key behind that one. Okay, next type of example, and a lot of these I'm giving just so I can explain the situation, like what is meant by some of the wording. A car goes through a valley with a radius of curvature of 100 meters. The car goes at a constant speed of 30 meters per second. What is the magnitude and direction of the car's acceleration? Now, the key here is that by direction, towards the center of the circle, while technically correct, is not going to be sufficient. Like what you need to demonstrate here is that you have a clear sense of whether or not that acceleration is going to be, like from the perspective of the driver, which direction is he accelerating? Because he doesn't really perceive himself as driving in part of a circle. He perceives himself as just driving on a road that happens to be going through a valley. So basically, what I mean by this is if you have a car that's, I'll do it a little bit more exaggerated just so I don't have to draw. If you have a car that's, and I'll be clear about this, at the bottom of the valley. Basically what it is indicating is it's indicating you have some situation like I've drawn down here, where you have your car like so, okay? And the car is going at 30 meters per second. Now, the idea is that this valley constitutes part of a circle. And if we were to, extend this circle, basically the radius of that circle would be 100 meters. Drawing certainly not to scale, but that's the idea of what's going on here, okay? So the key here is that you have to realize that A, this path is part of a circle, and that B, given that the centripetal acceleration is always directed towards the center, the acceleration in this case will be up. Okay, acceleration is up. Okay, so that's the thing you need to recognize, that towards the center of the circle, the acceleration will be up. Now, finding the magnitude is a piece of cake, just v squared over r, and you're given both of those. So it would be 30 squared over 100, which would be 900 over 100, which would be 9 meters per second squared upward. Now, the as to what this feels like, a lot of people splashed coffee on myself. That's no good. A lot of people have a non-intuitive or it's a counterintuitive idea to how this actually feels. But if you've actually traveled through a valley in this manner, or even just a little dip in the road, you might have a sense of what it would feel like. A lot of people will say it'll give a feeling of weightlessness. It's actually the opposite. You feel heavier when you're doing this. And I want to do another example to kind of show the, why that's the case. So this would be another example. A car travels over a hill. And I'll actually just use the same numbers with radius of curvature 100 meters at a speed, radius of curvature 100 meters at a speed of 30 meters per second. What is the magnitude and direction of the car's acceleration at the top of the hill? Okay. Now, this is something that I think is a little bit more common. You've probably experienced this and you know kind of what it feels like when you crest a hill. It feels kind of like your stomach starts to float a little bit. And, if you take it really fast, the car leaves the ground. So that's what's going on here. We'll get into why that is when we get into a force analysis, but I just kind of want to show you what is meant by this idea is that now what we've got is we got a hill and the car is up here at the top of the hill. I didn't draw it quite at the top of the hill, but you can imagine it's, at the top of the hill. But the idea is that now this hill is a part of a circle that extends downward into the ground. And the idea is that, that circle would have a radius of 100 meters. So again, we already know that the centripetal acceleration is 9 meters per second squared because the numbers are the same. It's still just v squared over r. I gave you, 30 squared over 100. And so there you go. That's how you'd get that. But the point here is that now, because this car is basically on the other side of that circle, now the acceleration is down. So the acceleration is that way. All right. So acceleration is down. All right. And that feeling of weightlessness you get it results from the fact of the interplay of the forces to generate this acceleration. We'll get into that a little bit more, is now down. Okay. We'll get into that a little bit more tomorrow. But the point is you have this feeling of almost weightlessness, not quite, but almost weightlessness as you would crest a hill at this speed. Now, it turns out your car would not quite leave the ground. We'll look at the condition for which that's true in the next lecture. But hopefully, if you've experienced this feeling of weightlessness, you'll buy that in the opposite situation, when you're doing a part of a circle, but on the other side, it will basically feel it'll feel like you have an increased weight effectively. Okay. So that is what is going on there. All right. Now, last one I wanted to look at is find the centripetal acceleration of the Earth and I'll say assuming the Earth has a circular orbit around the sun with an orbital distance of 148 million kilometers. Okay, so one of the things we're given, if we want to find this centripetal acceleration, we know that we're going to have to use v squared over r. And the direction, we know it's towards the sun. Like that's no big deal. That one kind of makes sense. So v squared over r. We know that r is equal to 148, and I'll write this out. That would be 1,000 million kilometers. Well, if we want to turn this into meters, basically we just need to add 3 more zeros. So this is 148 billion meters is basically what this is. Now, I would write it as 1.48 times 10 to the 11th meters. I think that makes more sense. It's a little bit more concise. So there we go. Now, how to find speed. So we are not given this. However, we know that, assuming uniform circular motion, this should be constant. So if we can get the known distance, some known distance that the Earth travels in some known time that the Earth travels it in, we can get a speed, okay? Because speed is constant, we don't have to worry about it changing. But this would be how we'd find speed. Now, see if you can come up with, just from what the information is given here, and then from some other common knowledge, see if you can come up with a known distance it travels in a known time. Pause it and check that out. Well, if you either didn't pause it or you're back, the answer is that you can say it travels one circumference or one orbit, circumference of a circle in 1 year. Okay, now we want to turn this into SI. So basically this will be 2 pi r over will over the time where t time is 1 year. Okay, I'm gonna leave that as capital T. The reason is a lot of times the capital T means period, and this just means period of rotation. Now, before I go too much further in finding these numbers, and we know that T is equal to 1 year, so we'll convert those units eventually. But before I go into these numbers, what you could do is you could say I would probably do some analysis first. So I'd say the centripetal acceleration is equal to v squared over r. Well, that would be 2 pi r squared. No, sorry, 2 pi r over t squared over r. Algebraing this out a little bit, this is going to give us 4 pi r squared, 4 pi squared r squared, sorry, not just 4 pi squared r squared over 4, and or over t squared. I think I might have made that mistake earlier. I was hurrying through the calculations. And then that r in the denominator, that just goes in the denominator there. Now, the key here is that one of these r's will cancel with that r. So you're really just left with 4 pi squared times r over t squared. Now, I'll go t equals 1 year. And you could do you could do 1 year, and then you could multiply this by 365.25 days per year for 1 year. And then you could multiply it by 24 hours per day. And then you could multiply this by 3,600 seconds per hour. Or you could just cheat and look up and Google seconds in a year. This is a constant, so seconds in a year. And it is 3.154 e to the 7. So equals 3.154 times 10 to the 7th seconds. Okay, so that's a perfectly fine way of doing it. Either one, I don't really care. Knowing this is how you get the conversion is nice, but you don't necessarily need to do that. So then your centripetal acceleration would then be 4 pi squared times 1.48 times 10 to the 11th over 3.154 times 10 to the 7th squared. Now, looking at orders of magnitude, pi times pi is like, it's about 10. That's pi squared is about 10. That's kind of helpful to remember. So, and then that's going to be about 40. So about 40 times 1.4 times 10 to the 11th, that's going to give us something times 10 to the 12th. This one is going to be 10 to the 14th or 10 to the 15th in the denominator. So we should expect something to be in the ballpark of 10 to the negative third. Just looking at the orders of magnitude here. So I'll go ahead and calculate that. So let's just do this. Okay. So 3.154 e7th squared 1 over x times 1.48 and 1.48 e11. Okay, times 4 times pi times pi. And what I end up with is 0.0059 meters per second squared. Okay, so the centripetal acceleration of the Earth, relative to the sun is actually quite small. Its acceleration, it needs to be quite small. And the whole reason is that that its direct, because its orbit is so large relative to its size, its direction doesn't need to change that much. Okay, so this acceleration due from the force of gravity on the Earth from the sun, it doesn't need to change it that much. Now, the force is actually quite high because the Earth is quite massive. And even to accelerate the Earth this much requires quite a large force. So, you know, at least relative to the forces we normally deal with. So that is something worth remembering. But nevertheless, that is what we would see there. So hopefully you found this useful. I'm going to go ahead and cut it there, but I will see you in the next lecture.